is we're going to talk about digital data modes, mainly on HF radio. That's where we're going to focus. What's happened is these days we've now got computers and sound cards and things, which make it very easy to try these different digital data modes. And so what we're going to talk about tonight is how you can get involved, and we'll go through some of the different data modes. So we'll talk about, first of all, what digital communication is about, how it, the basic principle behind what it's about. Then we'll go through. There's quite a number of these different digital modes, so we'll actually go through quite a few of the different options there that you can see. We'll talk about what you need to do at home in order to set up your station so you can get on the air and try some of these digital modes. And we'll talk about some alternatives as well. If you don't want to use a computer, then there's other options as well. So digital communication, first of all, communication in general, we normally have some sort of a transmitter here. In the old days we used to key the transmitter on and off with CW. So in modern transmitters we tend to generate a tone within the transmitter, an audio tone that then gets modulated. You can apply your voice. And so what happens is the audio comes into the audio stage of the radio, and we have a local oscillator, or a carrier oscillator in the radio. And when we mix the two, you get the sum and the difference of the frequencies. The main thing we're interested in here is the sum of the two frequencies. So your audio voice would appear down in this part of the spectrum, in the audio frequencies. And when we mix it with a carrier frequency, it actually gets shifted up into the radio frequency part of the spectrum. So this is quite a simplified diagram as to how a transmitter works. In practice, we often have a couple of stages. We don't normally go all the way in one go, but yeah, it works with voice. If we have a tone switched on and off, the audio oscillator, it causes a tone here to go on and off. And you can also plug your computer's sound card into this audio stage of the radio, and then the audio tones that get generated here get shifted up into the radio frequency part of the spectrum. So that's a basic principle. Is that more or less clear for everyone? Yeah. So we'll go to the... There's so many different modes. This is just a list of some. We're going to talk about quite a few of these tonight, just briefly, a quick introduction. Because there's so many different modes, how do you know which mode someone is using on the air? That's a big problem. Often you can tell by looking at a graphical representation of the signal, so we call that a waterfall. And often you can tell by looking at the waterfall, you can guess what the digital mode is. But it can be very difficult, especially if you're starting out. You really haven't got much of an idea as to what it could be. So there's this thing called RSID, which is Reed-Solomon identification. And that's a little FSK, frequency shift keying signal, that appears at the start of your transmission. And it's basically represents a code number. And so if you transmit that little standard burst, your RSID, before you start the actual transmission, then any other station who is listening can get the code number that you're using, and then they know which mode you're talking about. So if it sends number 23, that might mean it's Contestia 250/8 or something. So it's very important when you're playing digital modes, I think, to enable this RSID so that people can much more easily detect what mode you're using.
Matt, just quickly, are all these amateur modes, or are some of these commercial modes that have been tinkered with?
These are all modes which are used on the amateur bands.
Mm-hmm.
Some of these ones at the bottom, actually, I'm not familiar with.
I've heard them, but very seldom used. I think they are a little bit no-no-like.
Okay.
Yeah, so I'm only going to talk about the most common ones tonight, but there are some very obscure ones here which I haven't. This Stanag, for example, I've never heard of that one.
It's army. That's Russian army stuff.
Well, it came from the military.
Yeah.
Okay, so the first mode people usually start out with, and this is the mode that really made using your computer sound card with your radio really started the whole idea, is this PSK31. So PSK stands for phase shift keying, and so if you transmit a carrier signal and then you swap the phase back and forth, then you can encode binary ones and zeros. So you can encode numbers on it, and then you can use that to transmit information. So this is really one of the most popular modes on the band. It's quite a narrow bandwidth signal. So the rate at which they switch the phase back and forth is 31.25 times per second. And so that's where it gets its 31, so 31.25, just round it down. So PSK 31, and that means that that's the theoretical bandwidth of the signal as well. And so it's quite a narrow bandwidth, only 31 hertz, which means that it's quite a high power density. So if you put out 5 watts, that 5 watts is concentrated down into such a narrow bandwidth, it means that the signal, the signal's noise ratio is going to be very high at the other end, because you can filter out all the noise either side of the signal, and you can get good copy. It's the same reason that CW is such a power efficient mode as well, because again you're concentrating the radio frequency energy into quite a narrow bandwidth. So if you use a filter, you can get quite a high signal to noise ratio. And another similarity PSK has with CW is that the length of the different codes varies. So you know in Morse code, if you send an E is the most common letter of the alphabet, that's just a single bit, very quick to send. Whereas something like a number 0, that's da 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 da. It's quite a long time, and it occurs much less frequently. So PSK does the same trick. Letters that are most commonly used have only a short code, so they get sent fairly quickly, and letters that are less frequently used are a bit longer. Now, this here is a waterfall. So basically, it's like a frequency spectrogram of the passband out of your radio. So your radio, SSB radio, normally has about a 3 kilohertz bandwidth, because voice takes up to say 3 kilohertz. Good communication quality with voice, I mean. So a lot of radios will go up to 2.5, 3 kilohertz. So here you can see you've got the frequency along the top scale. So here we've got 200 hertz, there's 1000 hertz, a kilohertz, 2 kilohertz. And so you can have lots of these PSK signals being picked up by your receiver at once. And so with the computer you can click on one particular signal that you're interested in, and the computer will decode it. And I'll show you a program a bit later where the program can actually decode all the signals at the same time, and you can have a ticker tape, like in a stock exchange, of all the different conversations going on at once. So that's really quite interesting to see. So 20 metres, 14070, that's really the most common place to start with. It tends to work better on the higher bands rather than the lower bands. Lower bands have more static and noise, so there's probably other modes that are more appropriate for the lower bands, but 20 metres, that's definitely the place to start with this mode. So any questions on this? Okay. Now, another mode that's still very popular on the bands is radio teletype. And this went back to the days when, even before computers, they had these mechanical teletype machines that would generate these mark and space tones. So it's been around a very long time, and it's still very popular today, because for some reason in the contesting, when people use digital modes, radio teletype is really one of the most popular modes used in digital mode contesting. Some of the other modes are becoming more popular now. PSK is quite popular, and there's some other ones we'll talk about as well that are getting a bit more popular. But really, radio teletype is the grandfather of it, and so it works by using frequency shift keying. So the previous one we talked about swapping the phase of the signal. Here we have two tones, so I forget what the exact tones are, but they're spaced by about 170 Hertz. So by switching back and forth between a high tone and a low tone, you can generate binary ones and zeros and represent your different characters.
Are the characters all the same width?
Yes.
RTTY?
In this mode they are,
Okay.
so that they use something called Bordeaux is the encoding that they use. And how many bits is it? Is it 5 bits?
5 bits.
5 and
One check bit?
2 check.
Two
1 or
check
2.
bit, yeah.
It's 5 bits, but yeah, plus
But
some.
well, actually, yeah, you're right.
Yeah. So yeah, the check bits are quite good because it can detect when there's a mistake in the transmission. If you decode the tone incorrectly, then the check bit won't match, and so you know that there's a fault. So that's what's known as forward error detection. And some of the modes are even so sophisticated that they can work out which bit was incorrectly received, and it can fix it. So if it can fix it, that's now called forward error correction, which is really good. So we'll talk about that in some of the upcoming modes. Pactor is become quite a popular mode amongst the sailors. So
And amateurs.
amateurs as well. So Pactor is quite an efficient mode in terms of transfer rate versus bandwidth, so that they manage to transmit quite a large amount of data in a small bandwidth. And so this makes it quite interesting for things like using mailbox systems. So they have this WinLink 2000 system where you can set up an account.
I should point out there is a Pactor 4 now, and also Pactor and some of these IRQ modes. You send the thing and you get acknowledged that already the packet was passed, so it goes back and forth. Where the PSK or RT, it's one way and back. That's the major difference with these things.
Yeah, so some of these modes, that's true. They'll send something, and then the other end has to acknowledge and send back a transmission. So it chirps back and forth like a bit of a cricket or something. And when we use that method of correcting errors, we call that backward error correction, because the receiving station is actively telling the transmitting station that it needs a retransmit on something. So that's another way to deal with errors in the transmission. So the thing about Pactor is it will keep on sending back and forth. If there's errors, it will keep on retrying until eventually the message gets through. So it's quite good. And over in the US, they use it in the emergency. What do you call it? The amateur radio emergency services support. They like this mode as well. The downside of this mode is that you need to actually purchase a special hardware modem device, so you can't use the sound card on your computer. So you are forced to buy an expensive piece of equipment to play with this mode. But there is another mode that's a bit similar called Winmore, and that one you can use your computer with the sound card modems. That's fairly cheap. And some of the gateways that do Pactor, they'll also listen out for a Winmore signal, and if you try to communicate with them using Winmore, they'll fall back to that. So you can still play with Winlink and so forth using this Winmore mode, which is probably a good thing to do if you're just starting out.
Is the reason why do you actually have to buy that hardware device? Is it a proprietary chip?
Proprietary, yes.
It's proprietary?
The encoding is proprietary, and also
The Pactor one is actually in public.
Okay.
But you still have to have a box because computers they are not good enough on timing.
Right.
So you have to have a dedicated box to send,
To do timing.
receive, send, receive. And Pactor one is in public domain. But for the others, that's all box.
yeah, the latency requirements, everything are quite stringent, so it's not practical to do it with a sound card. So here we have MFSK 16. We talked about radio teletype where you've got 2 tones. Well, you can actually use more than 2 tones, and that allows you to cram more information into the channel. And so you can get a faster transfer rate. The other thing you can do is if you're able to send more information, you can send more redundant information which has error correction. So that it means that you can, if the signal quality is poor, then because you're sending a lot of redundant information, the receiving end is more likely to be able to pull the signal out of the noise. So on the HF bands where you've got lots of static and fading and multipath, things like that, the multi-frequency shift keying is probably one of the better communication modes when you're dealing with poor quality signals. So there's quite a number of different modes which are based around this multi-tone frequency shift keying, and we'll talk about some of the others a bit further on. One good thing about frequency shift keying is that your radio is only transmitting one single tone at a time. And what that means is that if your power amplifier stage isn't linear, that's not such a big issue, because if it's not linear, you can get harmonics, which you can filter out, but you're not going to get intermodulation because you've only got a single tone. So it means you can get by with Class C amplifier, for example, or even Class D mode that I think they're using on the new 630 metre band. It's quite common to use a Class D amplifier. So there's some good advantages for this frequency shift keying method. The phase shift keying, the linearity becomes extremely important, and the power output also varies a lot. The peaks and troughs. So linearity in a phase shift keying system is quite important. It's less important in the frequency shift keying. Okay. Hellschreiber is they say it's the oldest digital mode, back in 1929. I think it was created by the Germans, judging by the name.
It was too.
So Hell in German would mean light, and Schreiber is to write, I guess. So it's actually not a digital mode as such. It's actually using something like a fax technology. And so it's using more of an analog signal which draws out the letters of the message that you want to send.
CW, really.
It's more of a CW, is it? So the idea is that you basically receive an image, and then it's up to your brain and your eyes and your brain to look at the message and try and look through all the noise and corruption and decode the message. So you're actually using the filter inside your head to get rid of all the noise and try and recover the message. So they still use this in some contests. It's a bit of a
14063. It's if you listen there for a day, you probably find somebody there.
It's kind of fuzzy. If you did it long enough, I reckon your ear would pick out words.
You're right. You're right.
Yeah. Patrick and I had a QSO in 1929, didn't we, Patrick?
Yes.
okay, a bit before my time. So another mode that also isn't really a digital mode, but it's often done with these sound card modes, and I included this slide because I know some members were recently doing some slow scan TV, and so basically what you're doing here is you're using a tone to which varies in pitch in order to encode light and dark pixels in the image. So you scan one line at a time, and as the pitch goes up, maybe it's brighter, and the pitch goes lower, then it's darker. And so basically it draws out the picture. So the two most popular modes are this Martin M1 and the Scotty S1. So I think the guys the other night were using the Scotty mode to send pictures to each other. Originally the pictures were about, I think they had 120 lines. But these new modes, I think they do 256 lines, and I think maybe 16 of them are
320 and 24.
There's different modes
Yes.
with different resolutions,
Yes,
right the way up to
you're right.
stupidly large.
I think the Scotty and Martin, they are about the same.
But these seem to be the most popular ones. I think they're 320 by 240 or something like that.
Yeah, so there are different ones, but they are actually analog modes in a sense. So there is also digital slow scan TV, which is using this digital Radio Mondiale, sounds like a French name, which is being picked up by the shortwave broadcast stations to transmit their broadcast digitally. And there's also a sub-mode of this DRM, which allows you to transmit pictures. So some hams are playing around with that. And if you tune up to 14233, you'll hear some of this digital slow scan as well. Packet radio. So this was quite popular in the 80s, and I guess in the 90s the internet started to take over, so it became a bit less popular. Basically the idea here is that you divide the information you want to send up into packets, and so you just send a small part of the information. You send that first, and then you get an acknowledgement back, and if that one was received okay, then you send the next one. And there's some standards around this where you listen first to the channel before you transmit. So you only transmit if you detect the channel's free, and occasionally two stations will still transmit on top of each other by mistake. I mean, that just happens from time to time, but the packet protocol has a way of detecting that there was a collision, and then the packets will be retransmitted. You'll wait some random time before you retransmit. So it's actually quite similar to the way the internet works today. But packet radio is designed for unreliable radio links, whereas internet these days tends to use much more reliable transfer mechanisms. So you can still log into these mailboxes, which may be on HF, or a lot of the packet happens on the VHF 2 metre frequencies as well. So you still do get these bulletin board systems where you can send messages to each other and to hams all around the world. But the biggest use of packet radio these days is using this APRS, automatic packet reporting system. And this is where you send a packet out into the ether with some information such as your current position. You might have some telemetry information about how much fuel you have in the fuel tank in some remote generator. So you can use it for all sorts of different things. A lot of guys have their packet stations connected to a weather station, so it'll send out the current temperature and wind speed at a particular location. So APRS is quite an interesting mode. So I actually want to give another lecture a bit later this year about specifically on packet radio and this APRS, because it's quite an interesting topic, and unfortunately we don't really have time to go into it here. But like I say, you can hear it on 2 meters. It usually has a speed of 1200 bits per second, is quite popular. Occasionally you can get high speeds like 9600 baud. If you're doing satellite work, they tend to use that high speed. And if you're on HF, it's generally 300 baud, so it's a lot slower on HF. It's a fun mode, so I'll talk some more about that some other time. Olivia is another flavour of this multi-tone frequency shift keying, but the thing about this is it's very resistant to fading and interference from other stations. So if you have a signal to noise ratio of something like minus 15 dB, Olivia can still pull the signal out of the noise. So that's pretty impressive. I mean, a good CW operator, how low could they go?
Depends on their ears.
Depends on their ears. Zero dB signal to noise ratio is already difficult, and to go much lower than that, you'd be really struggling. So to be able to pull a signal out of the noise at minus 15 dB is quite an impressive feat. This mode is extremely slow, so it'll send 3 characters and then another 3 characters and another 3 characters, and you go and make a cup of tea, and then maybe the guy's finished his over. You can.
Suits perfectly to my typing.
So it's very slow, but it makes very heavy use of what I call this forward error correction, where it sends a lot more information than it needs to in order to get the message across. Just a simple example of forward error correction, we often do this in CW, is you send the message twice. So often if the conditions are really bad, you'd send a word and then you'll repeat and send the same word again, and so you'll double up on every word you send, so that the operator will hopefully get one of them, or he receives the first one and you can double check it when you send it the second time. So but Olivia uses a lot more sophisticated methods to send that redundant information. There are also different flavours of Olivia. The number of tones and the bandwidth. So that's the disadvantage of Olivia, is there's so many different types, and you really want that RSID feature in order that you can work out which exact mode they're using. The other disadvantage of Olivia is, or in fact multi-frequency shift code signals in general, is that you need to be fairly accurate in tuning into them. So Olivia is not too bad because they actually space the tones fairly widely, and so you've got a bit of tolerance. Plus the software can often detect when the signal drifts a bit, but you still need to be fairly accurate with your tuning. And so that's a general problem with MFSK modes. And there is a new mode actually which addresses some of that. So one mode that's definitely worth looking into is this one called Thor. So you know that static on the band is caused by thunderstorms, by QRN. So Thor was the Greek god of thunder. So this mode is the king of QRN. So it's really good on the low bands. The decoding ability is similar to Olivia. Often it will work when Olivia doesn't. But there are cases where Olivia will work and Thor doesn't. So a lot of these modes are, it depends on the exact conditions as to which one's the best. But the advantages of this one is that it doesn't use the exact tone to encode the binary ones and zeros. It uses the difference in tones, uses a sort of delta. And what this means is it makes it very immune to drift. You can even be turning your VFO knob while the signal is playing, and the computer will still be able to decode what you're saying. So the frequency stability of your radio the requirements are a lot less for this particular mode because it uses this differential frequency shift key. The other thing about this is that it's fairly quick. When they designed it, they wanted to make sure that you weren't waiting ages and ages like you are with Olivia, so they made it a lot more snappy turnaround time. With Olivia, when the guy finishes typing, the radio could still be transmitting for another 30 seconds, 1 minute, something like that, before it actually comes up on your screen at the receiving end. So Thor is meant to be a lot more snappy and interactive, and they use some other tricks to get the reliable encoding. Thor is actually very closely related to this mode called Domino X. So you may hear Domino X in the 80 metre contest that's coming up this weekend. Domino X 11 is one of the modes that is approved for that contest. So it'd be interesting to give that one a go. There's this automatic link establishment protocol. It tends to be used in the military a lot. But it does appear on the ham bands as well. And this is where the radios will be scanning the frequencies, a particular set of frequencies. And it has something like a cell call type of feature. So if you want to talk to a particular station, then you pick a band and you broadcast that station's cell call ID using a bit like an RSID type of arrangement. And the other station is scanning, and when it hears its own cell call signal being put out, it will respond. And so this system will try to pick a particular band where it works. If it doesn't work for one band, it'll try a different band. So the person who's operating the radio doesn't need a lot of special knowledge on HF techniques. They let the radios try and find the best communication. JT65, and there's a newer one now called JT9, which is optimised more for HF bands. Originally JT65 was written by a guy called J. Taylor, that's where the JT comes from, and 65 because it's got 65 tones. So you've got this this low tone is a sync tone. It always comes back to the sync tone, and it keeps on playing these other tones and back to the sync tone. Now, originally they designed this mode for 2 metre operation to do Earth, Moon, Earth operation. And so it works down to something like minus 28 dB signal to noise ratio. So it's even much better than the Olivia mode I mentioned before. The downside of it is it's quite slow. So basically, the other thing is you need to transmit exactly on the start of the minute on the clock. So all the people need to be synchronised to a common clock, and they usually use the internet to synchronise the clocks on their PC. When you've got a really weak signal, it's easier to be able to decode it if you know that there's something there. So if you have some idea as what to expect, it helps you to be able to decode that signal. And so JT65 relies on that. it knows exactly when the other person will be sending. So it's listening very carefully for the other person's signal. So normally what you do is you transmit for 48 seconds, then the system's got 12 seconds to decode, and the operator's got, at the other end's got 12 seconds for his computer to decode the signal he just received, and then decide on what he should do next. Should he retransmit what he sent last time, or should he move on to the next thing? And the exchanges are quite basic. So basically you send out a CQ with your call sign and your grid location.
Limited to 13 characters.
Yeah, it's limited to 13 characters, or they've got some tricky techniques. They can actually squeeze a few more in there for standard exchanges. So send out your call sign with your grid square. Someone will come back with their call sign and a signal report. So then you send a signal report back to them, and they'll say Roger, or if they didn't get it, they'll resend their signal report. So once you hear a Roger from them, then you send 73, and that's the end of the contact. So it's not meant for conversations. It's really meant just to make that contact, exchange a signal report, and finish. Whisper is written by the same guy. It's pronounced Whisper. With this mode, it's very narrow bandwidth, even less so than PSK31. It's a 6 Hz bandwidth, so that means that the rate at which you can modulate the carrier is very slow. And here you transmit for 1 minute 54 seconds, and nearly 2 minutes you're transmitting, and basically all you're transmitting is your call sign and grid square. And then other stations around the world are listening out for that beacon from you, and if they hear you, they'll upload onto the internet the fact that they heard you, and they'll put a signal report up onto the internet. And so then all these reports that are collected, you can then plot on the graph, and you can see a particular station, who heard you, and what signal to noise ratio they heard you at. So it's really good for testing propagation characteristics. You can see where the band's open. This works down to about minus 28 dB signal to noise ratio. I said that for the JT65, but actually JT65 is not quite that good. I think it's maybe minus 18 rather than, yeah, this goes down to minus 28, which is phenomenal. And one of the reasons for that is because of the extreme narrow bandwidth. So you can really get a very high signal to noise ratio. The important thing is the stability of the transmitter. Because the width of the signal is only 6 Hz, if your transmitter is drifting 10 Hz even over the course of that 2 minute transmission, then it's going to, you're going to see it on here. The signals aren't going to be straight and horizontal, they're going to be going up at an angle, and you won't be able to decode. So within that 2 minute period, I think you've got a tolerance of about 4 Hz or something you've got to stay in order for the signals to be reliably decoded. So it's it does put some stricter requirements on your transmitter.
Looking at the map on their website is quite good, just to very quickly see which bands are open.
Yeah, it's magic for that, isn't it?
Yeah, it's a great tool. Okay, so except for the Pactor, I already mentioned you need some special hardware. All these other modes I've talked about, you can just use sound card on your computer. So have a radio, sound card, which may be built into the PC, or it's usually better to use a separate external one. And the reason is because often on your PC you hit the wrong button and it has bells and whistles, or email arrives, you get some ding. You don't want that sort of stuff going out over the air. So generally you keep the sound card in your computer for playing all that noise that normally gets generated, and use a separate sound card for the radio communication. And that's exactly what I've got here. See, I've got exactly that same external sound card. So it's plugged into my radio here. and then into the PC. And so that's pretty much all you need.
And a PTT interface.
So the computer, you need something a little bit decent. I mean, these requirements aren't very strong these days. Most modern PCs would easily do it. But if you've got a very old PC, it may not be fast enough to be able to decode the signals properly. You can use Macintosh as well, modern sort of iMac. And as they make the point again here to use an external sound card if you can. So with the sound card, basically the computer is digital and the radio is analog, so you need to move from the analog world into the digital world. And that's what a sound card does. It basically has inside a analog to digital converter. So you want a reasonable quality one in order to preserve the quality of the signal. Most sound cards are usually quite good enough. If you want to do software defined radio things, then often you need to have a stereo external sound card. So this particular one here is stereo. But if you're just doing the basic modes that we've talked about, usually monos is okay. And a lot of the really cheap little USB dongles you get are mono only. But yeah, if you want to do software defined radio type of applications, make sure it's a stereo sound card. Usually they plug into the PC over the USB cable, and higher sampling rates are usually better. So depending what you want to do, I mean 48 kilohertz is a good speed. 96 is possibly better, especially if you're doing SDR applications. If you're doing SDR, you want at least 96 if you can. Okay, so there's a problem with using sound cards that I'll talk about a bit later, but there's some companies that actually make these interfaces that some of them have sound cards built into them. So they'll plug into the USB port of your computer and they'll present themselves to the computer like they're a sound card, and they'll plug into your radio. And they've got some special isolation and things inside to preserve the quality of the signal. The other thing is that the radio needs to know when to transmit. So you need to somehow work out how you're going to get the radio to go into transmit mode. So what some of these do is they have a Vox circuit inside. So if they hear the computer trying to send a signal, then they'll have a line that goes to the PTT port on your radio, and they'll turn the transmitter on. You can do that. What I'm doing here on this radio is this radio's got a Vox capability built in. Most modern transceivers do have a Vox circuit in there, so you can use the Vox on your radio as well. Or the other possibility is you have a serial port on your PC and you use the signal from the serial port to trigger the radio. So there are commercial solutions which take care of all this for you, which you can buy in the shop. And basically they're doing what I said. So the transceiver has audio. You've got audio into the transceiver for transmitting. You're getting audio back out of the transceiver for receiving. And so this goes into the sound card on your computer. And then you often do have a serial port on the computer, which may be used for keying the transceiver. So there's certain lines in your serial port that you can use to trigger the PTT circuit in the radio. And sometimes the serial port's also used to control the radio itself. So then your computer knows what frequency the radio is on, and it can control what frequency the radio should be tuned to. So you can make your own interface. So it's just a simple transistor switch circuit. So you use one of the lines on the serial port, switches the transistor on. You've got some protection diodes to stop reverse polarity and if you get voltage spikes from relays and things, and into the PTT port on your radio. So you can also make your own. One of the problems with making your own is you've got this problem with ground loops. So if you've got a computer that's plugged into, say, the AC, it's earthed, and your radio has also got a connection to earth, and maybe outside you've got an earth connection staked down into the ground to protect your antenna against lightning. So the equipment can be connected to earth in a number of different places, and the connection between these different earths, there can be some resistance. Then when you plug the radio into the sound card on the computer, you've got the ground line in your audio line, and so now there's a DC path via the mains earth or via the ground outside, and you've got the signal lines as well. So you've actually formed a loop here. And the problem with that is, you remember Faraday's law, where if you've got a loop of wire or something, and you have a magnetic field that goes through that loop, and the magnetic field changes, then it causes a voltage to be generated in the loop. And one of the problems is, around here, you've got the 50 Hertz mains, has magnetic fields that will go through this loop. And so this ground loop will pick up noise such as 50 Hertz hum from your mains, and it'll cause voltages to be generated in your grounds, and that actually shows up on the signal. So that's not desirable. You need to break this loop sometimes, and you can do that with the audio connections. Because audio is AC, you can use a transformer, so there's no DC connection anymore. It's just AC. And if you've got connecting up the PTT line in your radio, you can use a opto coupler solid state relay sort of arrangement. And those commercial interfaces often have this type of circuit inside to make sure you don't get this ground loop problem. There's a whole range of different software, so you can have a look. A couple of programs. FLDigi is really the main one for keyboard-to-keyboard chat, so that's the one you should definitely look at if that's what you want to do. Is chat to other people using text on your keyboard, and that supports most of the modes that I've talked about tonight. Doesn't support ones that do images, for example. So slow scan TV it won't do, and JT65 it won't do, because that's a specialist mode. So if you want to do JT65, especially on HF, recommends this program, JT65 HF, and they've set it up so it's quite simple. So you just basically push the button, you say call CQ, and it'll send out a CQ. Here you see someone sent a CQ, it's made it green so you can see. So you just double click on that, and then it will send back your call sign, your grid square, your current, it sends their call sign, your call sign, and your grid square. And there can be a signal report there as well. So you basically just click and you answer the call, send Roger, send 73 at the end of the QSO. So it basically just guides you through. You're just clicking on the buttons as you go through the different phases of the QSO. So it's a good program. Slow Scan TV. This is the one that I think the guys were using.
Yep.
In the past week.
Still the best.
So it has the Scotty modes I talked about, the Martin modes, if you remember, and some others as well. So they reckon that's the go-to one. And if you don't want to use a computer, you can actually buy little boxes like this that you plug a computer keyboard into, you can type, and it will generate all the tones and do what your laptop is doing. So you don't need to carry around a big heavy laptop, you just have a little convenient thing like that. This is called the Newing PSK, so you can have a look at that. And some radios these days even have that type of thing built in. So the KX3 here, for example, you can use the Morse code paddles to type in the text, and it will send it out using digital modes and print the answer back up on the screen. So there are some other modes as well. The important thing with these signals though is you need to get the levels right. Otherwise you can get distortion, and that's particularly important with PSK. As I mentioned before, linearity is very important with phase shift keying. So here you can see you've got the ALC, automatic limiting control, in the transmitter. When you see some activation there, what it means is that there's a feedback loop inside the radio that's reducing the gain of the transmitter because otherwise the signal's too strong. And so whenever you wind back the gain of the transmitter, you're now affecting the linearity. So having ALC indication is usually very bad, especially for modes like PSK. So whenever you do digital modes, you generally want to make sure you have no ALC action. Now there are some exceptions to that, like with the Yellowcraft radios, where there's some different rules, but for the most part, for most radios, you want to make sure that there's no indication of ALC on the display. So generally you wind back the volume coming out of your sound card, and you just increase it, and then when you see the ALC go up, you just go back a bit, and then you're sweet. If you do overdrive it, this is what happens. So you can see here we're getting clipping, and so we're getting harmonics of the audio tones, and you get this. Normally a good PSK signal should be, that's a fairly reasonable one there. So it looks like the sort of railroad tracks. Here it's completely overdriven, so it's very wide like that. This one here is another bad one. So see all the different copies you've got, that's all copies of that same signal. So it's probably being badly overdriven at the transmitter. Could also be the receiving guy's also not got his side set up properly as well. But if the guy who's transmitting gets it wrong, then he's obviously spewing rubbish out over the bands. If your transmitter's not stable, frequency drifts, you get this sloping thing, so that the tone starts high, and over time the tone gets slightly lower. So that means the radio is drifting. So that's also not what you want. So that's basically the end of what I've wanted to say tonight. So different modes that encourage you to get on the air and give them a go. You can see the equipment's not terribly complicated. In this case, I don't have any special interface at all. It's just a sound card, plugs straight into the radio, plugs into the computer. I use the box on the radio to turn the transmitter on and off, so I don't have a separate keying line. And yeah, you can go on and play. So, any questions?
When are we going to start?
Is there a demo?
Yeah, well, we can do a demo. This lecture's probably run a bit longer than I expected, so we can have a look, see if there's any activity on the air. Yep, go ahead.
I've got a question. So, you talk about the ability to work into the noise. I suppose it offers the possibility for people to operate QRP, but my question is, do people operate QRP on this,
Yes,
or do they
yes,
run full
yeah.
electric? So it's really for QRP,
On
isn't it?
PSK, you're advised not to go over 60 watts out, full stop.
Okay.
And
Do
a lot of
people-
guys,
You don't get Americans running a couple of kilowatt or any of that sort of nonsense?
some maybe do. That was one problem. No,
You're always going to get. The problem is if you if one person transmits a very powerful signal, much more powerful than everyone else, what happens in your receiver is it activates your automatic gain control. And so now, basically, if there are any weak signals here, you won't hear them because the gain of your receiver has been wound back because of the strong signal here. So it's considered quite impolite to run kilowatts of power on some of these modes. You want to run a similar sort of power to what everyone else is running in order to keep it balanced and give everyone a fair go.
Is that considered shouting?
probably.
Well, it's considered being a lid, so.
But nobody runs more than 30 to 60.
Russell?
Yeah, man, I was just going to say, it's probably worth mentioning that while it's good to have the external sound cards and all that sort of stuff, if you just want to have a listen and see if you're interested, you can go with a cable straight from your headphone socket out to your sound card in, download MMS TV, Hellschreiber, Digipan, and hey presto, you can have hours of fun and then decide if you actually want to transmit.
Yeah, I should actually mention that. You actually don't need any physical connection at all. If you've got a microphone, put it next
That's it, audio link. Yeah,
put it next to the speaker of your radio,
Yeah.
and then you can decode on your radio and you hold the microphone of your radio up to the speaker on your PC and transmit. I'd say that there's more chance of having a dirty signal if you do that, but certainly if
You get echo from the room actually.
yeah.
It's just a simple 3mm cable socket to a socket and you're away.
If you have two computers at home, which most of us probably do, put the programs in, put them next to each other, and just talk to between those two, and you will learn the sounds of it. You will learn the operating how to operate it. You just do little sort of funny QSOs, and actually it's the best way to learn that stuff.
Do they count in competitions?
If you're flying off, yes. Same grid split.
So we might end the lecture there. We could informally have a bit more of a play if people want to have a look, and
We can
I
do
can show them the program. But yeah, I think here we'll end the formal part of the proceedings. So thanks very much.
Yeah, thanks a lot.